In the short, we asked whether a universe of typing monkeys could recreate Hamlet. In the next few minutes, I'm going to quantify two curves, the exponential growth of possible text and the finite resources our cosmos can spend in the effort. Then I'll pivot to enzymes and why this gap matters for the origin of life. Strip Hamlet to letters only, no spaces, no punctuation. Its length is about 142,953 characters. At each position, you can pick one of 26 letters. The number of possible strings is 26, raised to the 142,953rd power. Written out, that's roughly a 1 with about 200,000 zeros. It's not just big. The improbability grows exponentially with every added character. Now, what can the resources of our universe actually accomplish? Let's be wildly generous. First, conscript the cosmos, about 10 to the 80th atoms. Second, give each atom a keyboard and let it type 10 to the 20th characters per second, supercomputer speed. Third, let them type for roughly 10 to the 20th seconds, a rounded figure for the age of the universe in seconds. Multiply those together, rate times time times keyboards, and in the absolute best case, we get about 10 to the 120th total attempts. 10 to the 120th is colossal, until you compare it to the target space for Hamlet, which is on the order of 10 to the 200,000th. That's the mismatch. Every extra character multiplies the problem by 26, but our resource budget doesn't multiply with length. One curve rockets upward, the other stays capped. What does that mean for probability? The chance of typing out Hamlet on any single attempt is 26 to the negative 142,953rd power. Roll that chance across 10 to the 120th tries, and it's still so tiny that if you printed the resulting decimal, you'd flip through about 95 pages of zeros before you met the first one. No law of probability forbids success on the very first try, but overwhelming likelihood points the other way. Why bring biology into it? Typing Hamlet is a one-dimensional problem, letters in a line. A functional enzyme and its corresponding code are similarly improbable. The alphabet is 20 amino acids. The order matters, the chemical motifs matter, and the chain must fold into a precise, three-dimensional shape based on attractive repulsive forces across the entire sequence. That shape must further the process. Its job is to fight entropy. Usable targets are not just rare. They're rare and isolated among astronomical numbers of non-functional tangles. The search space is enormous, while physics and chemistry can only supply a finite number of trials. Enzymes are rarely functional by themselves. Most are part of a process. A fair note about chemistry. Real prebiotic processes aren't a perfect lottery. There are biases, surfaces, templates, and selections that can tilt the search. The point here is narrower. Pure randomness alone, without strong constraints, doesn't buy very much when the search engine grows exponentially and the trials remain finite. If random search is your only engine, the math is brutal. So what could close the gap? 1. A cosmos that's bigger than the patch we observe. Perhaps our Big Bang is local and recent, inside a larger, possibly infinite and eternal reality. That would change the resource budget. 2. Powerful constraints we haven't fully mapped. Pathways that funnel chemistry into narrow, high-value regions of sequence space. 3. Some combination of both. Back to the monkeys. This thought experiment is a measuring stick. It tells us when just keep trying can work, and when the math says you either need far more trials or time than our patch of reality offers, or far tighter guidance than a blind search can provide. In On the Origin of Enzymes, I examine the numbers and the models. If this helped, subscribe. Next, I'll quantify a single translation enzyme. And if you want the full argument now, read the book. The link is right below.